right, so we previously covered proportional damping. That was where we expanded the damping matrix into something like alpha m plus beta k, where alpha and m are just constants here, meaning that the mass or the damping matrix is proportional to the mass in the stiffness matrix. And this is what we'll say is a type of classical damping. It's also known as Rayleigh damping, and it's a common approach for modeling damping. Another one is to experimentally measure damping ratios for each mode, and then you form a damping matrix based on those damping ratios. Okay, so a classically damped system will possess classical normal modes, and that means that the modes have the same, or the mode shapes are the same as those of the undamped system. So if we have a classically damped system, we can solve the undamped eigenvalue problem to find the mode shapes and the natural frequencies, and those are still valid for the damped system as well. When the system is not classically damped, then we cannot do this, actually. And we'll deal with that later in the class when we deal with state space. All right, so equation 35 here is a sufficient condition for a system to be classically damped, but it's not the necessary condition, meaning that there can be other types of damping matrices that are classically damped. And the necessary and sufficient conditions are that the matrix M inverse K and M inverse C, those must commute, meaning that the quantity M inverse K times quantity M inverse C must be equal to M inverse C times the quantity M inverse K. And it says here that a system is classically damped if and only if equation 35 is true, but this should say equation 36. So the condition we just wrote, that has to be true for a system to be classically damped. Meaning that it will only give rise to mode shapes and natural frequencies that are identical to the undamped system if this is true. So another type of classical damping, like I mentioned, is one of modal damping. This is where you prescribe what the damping ratios are for each mode. Generally, you'd measure those from an experimental frequency response function, specify those, and then you would go and compute the damping matrix directly. So non-classically damped systems will result in complex mode shapes, and by that I mean real and imaginary, not like complicated mode shapes, but actually complex mode shapes. And what this means is that the displacements of the system are no longer in phase at different locations. We're not going to cover complex modes in this class. When we deal with non-classically damped systems, we're going to do it through state space formulation, and we're going to solve the state space equation directly. And we'll do that like a month or two from now. Yeah, and that's what I said in the last bullet, is that we're going to use state space coordinates to solve this, and we'll see that later. That's really all we're going to say about damping right now. Are there any questions on what we've covered so far? Okay, in that case, we're going to go on and we're going to talk about rigid body modes. So systems that are not sufficiently restrained are going to be able to move as a rigid body. That means there will be no deformation or flexible motion between the degrees of freedom. And we call that a rigid body mode. And rigid body modes will always have a frequency of 0. And in these systems, the potential energy can be 0 even if all of the coordinates are not 0, meaning that you can have a non-zero displacement but still have a 0 potential energy in the system. And so yeah, rigid body mode corresponds to motion where the entire system moves as one rigid body. And we're going to demonstrate this through an example. So we're going to consider a system with two masses connected by a single spring. The spring in the middle there just couples the two together, and neither of the masses are connected to the ground by anything, meaning that they're just kind of floating there in space. We're ignoring gravity, and we're ignoring any kind of non-conservative force, so no damping, no friction, nothing like that at this time. No external forces either, and we're going to go in and we're going to determine the natural frequencies and the mode shapes of this system, and then we're going to go and compute the transient response for a generic set of initial conditions for this system. All right, so the first thing we're going to do is we're going to write out our equation of motion, which is mx double dot plus kx equals to 0. In this case, our mass matrix would just be a diagonal matrix with m, 0, 0, m. The stiffness matrix is just going to have that single spring in every term, so we'll have k, and k here. And then our vector x was equivalent to, or is equivalent to x1 and then x2. No, they're functions of time. So these x1 and x2, they are the displacement coordinates, this and this right here. That's what they are. So x here is a displacement vector. So we can explicitly write that. It's x1 of t, x2 of t. From here, we're going to go and formulate the eigenvalue problem. We're going to solve that. It says for the undamped system, there is no damping in this system, so we're never going to involve damping. But nevertheless, that's still the first step. This is where we'll assume an ansatz, or assume a solution for x of t. We're going to use big X for its amplitude, and that's a vector of amplitude times e to the j omega t. There's no damping here, so we will certainly get oscillations. So this is a valid assumption. We can plug this back into our equation of motion, and we'll get minus omega squared m plus k times big X e to the j omega t equal to 0. And for this to be true and for it to be a non-trivial solution, we must have that the determinant of minus omega squared m plus k, that determinant must be equal to 0. So we can go and solve that determinant. We'll get here the determinant of the matrix k minus m omega squared, and then minus k in the off-diagonal terms, and again k minus m omega squared here. That must be equal to 0. If we compute this determinant, we'll find here that k minus m omega squared quantity squared minus k squared is equal to 0. This is going to give rise to our characteristic equation, which will then allow us to find the omegas. expanding this, we will get m squared omega to the fourth minus 2m k omega squared plus k squared minus k squared equal to 0. And then we'll eliminate the k squared terms. Leaving us with m squared omega to the fourth minus 2m k omega squared equal to 0. We can pull out an omega squared here. So we get omega squared times the quantity m squared omega squared in fact, actually, we can pull out an m. So let's start that over. We'll write here m omega squared m omega squared minus 2k. And all of that must be equal to 0. All right, what are the potential solutions for omega? And how many are there? 3, I see. Okay, 3. Why 3?
It could be 0, and then with the first term, and the second term, 7 equals 0. Can be positive, negative. I guess it can be negative, so it is.
Okay, so 2 options. We said first is that from this first portion we can find that omega is equal to 0, or you're saying that we can use the second portion, everything inside the parentheses, and you set that equal to 0 and solve for omega, which will then lead to m omega squared minus 2k equal to 0, or that omega is equal to the square root of 2k over m. We only consider positive square root because, again, negative frequencies do not make physical sense. So this omega equals 0 term, this gives rise to the rigid body mode. Whereas the second quantity, this gives rise to a flexible mode. And then this tells us then that the natural frequencies are first we'll have just omega 0 equal to 0, which is radians per second. That's our rigid body mode. And then we'll have omega 1 equal to square root 2k over m. So generally, when we have flexible modes, we will start the numbering of the modes from 1. If we have a rigid body mode, we'll start that one at 0. If we have multiple rigid body modes, then we generally will partition them and say this is our set of rigid body modes, this is our set of flexible modes. And we're going to see why we want to separate these, because they give rise to drastically different displacements. So at this stage, we now want to go and compute our mode shapes. And to do that, we're going to plug in the natural frequencies into the equation minus omega squared m plus k times big X equal to 0. We need to do this for each natural frequency and then find what the mode shape is. We'll start with omega 0, and I want you guys to compute the mode shape with your neighbors. And once you get it for omega 0, then I want you to go and compute it for omega 1 equals square root 2k over m. And I'll come walk around and give some input. So for omega 0 equal to 0, again, the equation we're trying to solve is minus omega squared m plus k times x equal to 0. This x here is equal to some vector x1, x2 transposed, and it contains the amplitudes of the displacements, or we're going to show it's going to end up being the amplitudes of the modal coordinates. Okay, so we'll substitute this in, and we'll get minus omega 0 squared m plus our k matrix times, we're going to call this x0 equal to 0. Omega 0 is equal to 0, so we're going to lose this entire term, such that we'll get the stiffness matrix times x0 equal to 0. You can expand this. We'll get k minus k minus k, k times an x01, x02. That's equal to 0, 0. From there, carrying out this matrix multiplication, we'll get two equations, k x01 minus k x02 equal to 0, and minus k x01 plus k x02 equal to 0. And these are the same equation, so we have two unknowns, one equation, meaning that we'll have an infinite number of solutions to these equations. And as a result, we can first show that x01 is equal to x02, so they have the same amplitude. But again, they're going to be scaled arbitrarily by some constant. So our mode shape we're going to write here is x0 is equal to the vector, and we're going to put a scalar in here. Let's just use sigma. We'll use a sigma here, and this is going to be 1, 1, where we're scaling arbitrarily by this sigma here. This also happens to be an in-phase mode, but more importantly, because they have the same amplitude, there's going to be zero relative displacement, meaning that the spring is not going to be compressed or stretched in this mode. Moving on to omega 1. Omega 1 is equal to the square root of 2k over m. We're going to substitute this in, minus omega 1 squared, that should be m plus k times an x1 in this case equal to 0. Here we're going to get k minus quantity 2k over m times m minus k down here, minus k up here. And in the last term, we'll get k minus 2k over m, also multiplied by m. All that multiplied by x11, x12, equal to 0, 0. From here, we're going to get two equations. Just like before, we'll end up with minus k x11 minus k x12 equal to 0. And here we get literally the same equation, k x11 minus k x12 equal to 0, such that we'll find that x12 is equal to minus x11 And then our mode shape is going to be equal to, x1 will be equal to, we're going to use a gamma here, some arbitrary constant, times the vector 1 comma minus 1, all that transposed as written here. We need to transpose up there. This is here an out of phase mode. Such that our modes of vibration are as follows. We have omega 0 equal to 0. We got x0 equal to sigma 1, 1 transpose. Omega 1 equal to square root 2k over m. x1 equal to a gamma 1 minus 1 transpose. And that is the set of modes of vibration or normal modes for this system. Okay, now that we've found our mode shapes, the next step, or modes of vibration, the next step is to mass orthonormalize them. We're not going to go through the steps here, but if you do it, you're going to find that mass orthonormalization results in the following. When we do this mass orthonormalization, we're finding a convenient value for those arbitrary scalars, in this case sigma and gamma. We're finding convenient values for that will help us when we do this modal decomposition. So it results in our first mode shape, phi0 equal to the square root of 1 over 2m times 1, 1 transpose. Phi1 here will then be equal to the square root of 1 over 2m times 1 minus 1 transpose, such that our modal matrix, or capital phi, is equal to square root of 1 over 2m times the matrix 1, 1, 1 minus 1. And that is our modal matrix. So from here, we're going to define modal coordinates, and then we're going to use them to decouple the equations of motion. We're going to start by letting our vector of displacements equal to our modal matrix phi multiplied by the vector of modal coordinates, eta, and then you can go and compute how the velocities and the accelerations relate to that. We'll then substitute this into the original equation of motion. That's mx double dot plus kx. And then pre-multiplied by phi transpose, and we'll end up with here phi transpose m phi eta double dot plus phi transpose k phi eta equal to 0. We do the mass orthonormalization such that this first quantity becomes an identity matrix, and the second quantity becomes a diagonal matrix of the natural frequencies squared. Such that we'll end up with two equations. We can write this as eta I double dot plus omega I squared eta equal to 0 for I equal to 1. should be 0 and 1. And then let's deal with our initial conditions, or the ICs. So eta of 0 is equal to phi transpose m times x at 0. Eta dot of 0 is equal to phi transpose m times x dot of 0. And here we're going to say that x of 0 is equal to, we'll have some constant x10, x20. These are lowercase x's, so they are the initial displacements, not the mode. They're not the mode shape. And then we'll do the same thing for x dot of 0. So it'll be a vector of, we'll say v10 and v20. And those are the initial velocities. From here, if you do the transformations, you'll find that eta of 0 is equal to the square root of m over 2 times the vector x10 plus x20, comma x10 minus x20, throw a transpose on that, and then eta dot of 0 is equal to square root m over 2 times a similar vector v10 plus v20 and v10 minus v20, all that transposed. The initial conditions? Oops. So I stated in the beginning of the problem that we were going to consider generic initial conditions, meaning just some value, some constant, and that's what I chose to represent those constants with. Okay, from here what we're going to do is we're going to split the two equations up. We're going to have an I equals 0, and we'll have an equation for that. We'll have an I equals 1, and then we'll need to solve for the motion of each of those modal equations. And you're going to do that with your neighbors while I come around. Okay, so a lot of people were lost, so we're gonna go through this. A lot of people were trying to compute initial conditions. We actually already did that. I just didn't write them up here in purple because they're different for each mode. So for I equals 0, what we're trying to solve here is the differential equation eta I 0. Let me rewrite that. Eta I 0 plus omega 0 squared times eta 0, that's equal to 0. The initial conditions here are eta 0 of 0 equal to square root m over 2 times x10 plus x20. These are just the initial displacement of each mass. And you'll note that this right here comes from the first entry right above there where I said what eta 0 is. There was a question?
Could you walk through how you got the square root of m over 2?
Yep. So I found phi, this modal matrix phi. I then went and I computed phi transpose times the mass matrix. And that's where I got it from. So I saved you guys some work, at least here, in terms of that. and eta dot of 0 is going to come from the first entry right above square root m over 2 times v10 plus v20. And now we need to substitute in for omega 0, and we need to solve this differential equation. We're going to get here eta 0 double dot plus 0 squared eta 0 equal to 0. We'll get rid of that term because it's 0. From here we get eta 0 double dot equal to 0. Maybe. There we go. Equal to 0. You can integrate both sides with respect to time, and then you'll find here that eta sub 0 dot is equal to some constant, just say c here. This is going to end up equaling to the initial velocity term. I'm going to call this q0 just to save some space. Let me move this over here. I'm going to call the displacement p0 just to save a little bit more space here. That's equal to q0. You then integrate a second time and you'll find that eta 0 is equal to, well, that constant times t plus another constant. That other constant is going to end up being the initial displacement, p0. And then we'll find here that the response of the first mode, or the 0th mode, eta 0 of t will be equal to the square root of m over 2 times the quantity v10 plus v20 times t plus x10 plus x20. And that is the solution for the first mode. And so what we see here is that the rigid body mode will cause the system to move horizontally for all time in a rigid fashion. If there's some initial velocity applied to either of the masses, then both of them are going to move horizontally forever in whatever direction determined by the initial velocities. And if there's some initial displacement, then they're just going to stay at those initial displacements for all time. If there's zero velocity but some initial displacement, they'll stay at that position for all time.
When you're defining A0 up top, you have x10 plus x20. Can you define what each of those stuff is?
Sure. So if we come back up here, we have an x1 at t and an x2 at t. So if we come over back down here, what I'm saying here, if you recall that the x vector is a vector of x1 and x2. So I'll write it over here in purple. We'll do right here. So x0 is equal to x1. Oops. My pen is not working. All right, I'm gonna write it on the board for you guys. Unless I can get this to work. Yeah. I'm gonna try to write on the board if I can find a marker, because I did not bring one myself. All right. All right. Now once it works, so we're just going to continue here then. So this is x1 of 0, x2 of 0. That's where they come from. So they're just constants. And then you can do the same thing for v10, v20 for the initial velocities. All right, any other questions? All right, I'll finish the rest of this problem in a pre-recorded lecture. However, the solution is down here, and I just wanted to show you what the total response looks like. You can see that there is an oscillation for each mass, and there's also a non-zero or just a rigid motion in time. Both of them are moving horizontally forever.